In this chapter, I'm going to talk about entropy changes and some of the factors that affect entropy, as well as one of the most important concepts in thermodynamics, which is free energy. So we'll start where we ended off in the last video and talk about the third law of thermodynamics, which states that the entropy of a perfect crystal is zero at absolute zero. In other words, the entropy of a crystal with no impurities, so this is a crystal that is composed of one single element. It is all arranged perfectly in a crystal. So the entropy of that crystal at absolute zero, which is 0 degrees Kelvin, is zero. So the entropy of that particular system is zero. And every single substance, no matter what it is, an element in a solid state, a liquid state, a gaseous state, is going to have an absolute entropy, and that is just the entropy of a substance at a temperature above 0 Kelvin. So remember, at 0 Kelvin, entropy is going to be zero, but at any value or any temperature above 0 Kelvin, the molecule or element is going to have some entropy associated with it. And that's because in something like a molecule, there are bonds which can vibrate, which can rotate, and the molecule itself can move around in space. So the movement of the molecule, the movement of the bonds, the movement of the electrons contribute to that particular molecule having an entropy value at a specific temperature above 0 Kelvin. Now, the standard molar entropy is the absolute entropy of 1 mole of a substance in its standard state at 298 Kelvin and 1 bar of pressure, and it's calculated from measurement of molar heat capacities as a function of temperature. So this table shows you what standard state means in different physical states. So a solid, to be in standard state, has to be a pure solid and the most stable allotrope of an element. We'll talk about an allotrope a little bit later if you don't know what that means. For a liquid, it has to be pure. For example, pure water. It can't be an aqueous solution, so it can't be salt water, for example. Gas has to be a pure gas, and solutions have to be 1 molar. And the pressure of all of these has to be 1 bar if it's at standard state conditions. So this table shows some standard molar entropy values for a bunch of different molecules. So I want you to notice a couple things. If we just look at bromine gas and bromine liquid, notice that they each have their associated standard entropy values, and the entropy for the gas is greater than that of the entropy for the liquid. That makes sense because a gas can fill up an entire room, whereas a liquid with the same number of moles as that gas, for example, would be confined to a puddle somewhere in that room. So the amount of space that the gas can take up is a lot greater than the amount of space that a liquid can take up, and that contributes to its greater disorder. Now, if we go down to the next two, there's carbon solid as diamond and carbon solid as graphite. These are the same element, obviously, carbon, but the crystal structure is different. Diamond is very rigid, whereas graphite is not quite as rigid. Okay, graphite is in your pencil, so you can easily scrape off layers of that graphite as you're writing on your paper, whereas if you do the same thing with diamond, obviously that's not going to happen. You're going to be cutting your paper. So since diamond is more rigid of a structure, is more ordered, it has a lower entropy value than graphite, which is a little bit more disordered. So you can look at the rest of this table and find other examples of compounds that are very similar but have differing entropy values based on their molecular structure or their physical state. So now we're going to talk about some trends in entropy and some of the factors that affect entropy. So if you look at just the physical state of an element or a molecule, the solid state is going to have less entropy than the liquid state, which is going to have less entropy than the gas state. So if we look at the entropy of water going from a solid to a liquid to a gas, we have the entropy on the y-axis and the temperature on the x-axis. And as we increase the temperature, the entropy of the ice or the solid increases to a point where it reaches 0 degrees Celsius. That is obviously the melting point of the ice. And at that point, the entropy increases quite a bit because now we're going from a solid state to a liquid state. Liquid state has far more disorder than a solid state. Keep on increasing the temperature in the liquid phase, the entropy increases further, and then we have this big huge jump right here where the liquid turns into a gas at 100 degrees Celsius, and then continuing to increase the temperature after that results in a continuous increase in the entropy. But you can see that the big increases in entropy come at the phase changes, so going from a liquid to a gas and going from a solid to a liquid. So these next few slides just give you some other factors that affect entropy. So we have a pure solid versus an aqueous solution. Obviously the solid is going to be more ordered than the aqueous solution. So the solid is going to have a lower entropy value than the aqueous solution. Molecules at lower temperatures also have a lower entropy value than molecules at high temperature. At high temperature, the molecules can move a lot more quickly than they can at low temperatures, and that's going to affect the entropy. If we're looking at a chemical reaction where we have 2 molecules on the reactant side and 4 molecules on the product side, fewer molecules is going to have less entropy than more molecules. So if we look at structure, the entropy increases as the complexity of molecular structure increases. That's because more complex structures have more bonds, more opportunities for internal motion, like vibrational and rotational motion. So if we have something like CH4 versus CH3, and so on and so forth, the molecule that is more complex and larger is going to have a higher number for entropy than the smaller, less complex molecule. So here we are back with diamond and graphite. These are called allotropes because they are made up of the same element, but they have a different crystal structure. So you can see that diamond has a very rigid structure, it is very ordered, and there's less range of motion for each of those carbon molecules within that structure. Whereas graphite is oriented in sheets, and each sheet has weak London forces between each of the layers, so they're much more easily moved than the structure of diamond. So when you're writing with your pencil, what you're doing is scraping off each of those layers of graphite and depositing them on your paper. So graphite has more entropy than diamond. So some other factors that affect entropy, we know temperature does. We talked about that one already. Volume affects entropy as well, because if we increase the volume of a container, then we're allowing the molecules to occupy more space, which results in more entropy. And we talked about the number of particles, the number of molecules. So entropy increases as the number of particles increases. So we can use these observations to predict entropy changes associated with reactions, and we'll do a couple of those. So now we're going to move into calculating entropy changes. And to do that, we use this equation here. So the entropy of the reaction is going to be the entropy of the products times the number of moles of the products minus the entropy of the reactants times the number of moles of the reactants. And we've seen this equation here already in the previous video, but I just want to point out something that will become important a little bit later, where Q of the system, or Q in general, is just the same as delta H. They both refer to the heat of the reaction or of the system or of the surroundings, depending on what this little subscript is. So let's do a quick practice where we are trying to calculate the delta S, or the entropy change of this particular reaction. So before we do the calculation, try to look at the reaction itself and predict whether the reaction will result in increased entropy or decreased entropy as the reaction goes forward. So remember some of the factors that affect entropy. We have the number of moles of each of the compounds in the reactants and products, and we also have the physical states of the reactants and the products. So here we have in the reactant side a total of 9 moles of gas. On the product side, we have a total of 4 moles of gas and 6 moles of a liquid. Now we know that liquids have lower entropy than gases, so if we look at this reaction as a whole, you could say that we have lots of entropy on the reactant side, and since we have fewer moles of gas on the product side and some liquid, we would predict that this particular reaction would result in less entropy, or a negative entropy value. So now let's try to see if our prediction is correct by calculating the entropy value using the information below. So the first thing we need to realize is that we will be using this equation here to calculate the standard molar entropy of this particular reaction. So then all we have to do is to look at our values for the products, which is the CO2 and the H2O, and their respective stoichiometry, which is 4 and 6 in this case. And for the reactants, we have C2H6, 2 of those, and 7 oxygens. So when we plug the numbers into the equation, we get what we see below. So the first part of the equation, 4 times 213.8, that's because we have 4 carbon dioxides, and each carbon dioxide is 213.8 joules per mole Kelvin. And then we're adding to that the next product, which is water. There's 6 of those, and each water is 69.9 joules per mole Kelvin. And then we subtract the reactants using the same process. And if we solve the equation, we get minus 619.4 joules per mole Kelvin. So that seems to make sense. We predicted a negative value for standard molar entropy for this reaction, and that's exactly what we get. So now let's talk about free energy and free energy change. And like I said at the beginning, this is one of the most important things in thermodynamics, because as you'll see, it allows us to predict whether a reaction is spontaneous or not just by looking at the components of the system. So Gibbs free energy is the maximum energy available to do useful work. So we're not going to talk too much about the work part of this in this class, but the energy of this reaction, or the Gibbs free energy, tells us how much energy is available to do work. So how much energy is available to power your cell phone, how much energy is available to run your car. And the free energy change is the change in a free energy of a process occurring at a constant temperature and pressure. And for a spontaneous process, delta G is going to be less than 0, or delta G is going to be negative. So the derivation of this equation on the bottom isn't that important, but I still want to walk you through how we get there. So we know that for a spontaneous process, when we look at entropy, the change in entropy of the universe, or delta S of the universe, is going to equal the delta S of the system plus the delta S of the surroundings. And if the delta S of the universe is greater than 0, in other words, if it's positive, then that means the reaction is spontaneous. But again, we have to know something about the system, and we have to know something about the surroundings. Now here's this equation again. Delta S of the surroundings equals negative Q of the system divided by the temperature. And again, Q system equals delta H system. So what we can do is we can substitute delta H for Q, and then substitute this new delta S surroundings for that delta S surroundings in the second law of thermodynamics. And that gives us our new equation down here. And then if we multiply by minus T and do a quick rearrangement and define this as delta G of the system, then we get this equation down here. Then we get this equation at the bottom, delta G of the system equals delta H of the system minus T delta S of the system, or delta G equals delta H minus T delta S. And notice again that each of these components, delta G, delta H, and delta S, refer only to the system. So we don't have to worry about what's going on in the surroundings. So for a system at constant temperature and pressure, if delta G is negative, then the forward reaction is spontaneous. If delta G is positive, then the reverse reaction is spontaneous. And if delta G equals 0, then the reaction is at equilibrium. So this slide just shows you some of the processes that favor a spontaneous reaction. So exothermic processes favor a spontaneous reaction because that results in the formation of low energy products. But of course we know that delta H cannot tell us whether or not a reaction is spontaneous or not, because reaction can be exothermic or endothermic and can still be spontaneous. The formation of products that have greater entropy than the reactants, so when delta S of the reaction is greater than 0, that's also a driving force for a spontaneous reaction. And free energy relates both the enthalpy and the entropy, as well as the temperature for that particular process. So the combination of delta H, T, and delta S is going to be able to tell us whether or not a reaction is spontaneous or not. So as with the standard molar entropies that we looked at earlier, each molecule also has a standard free energy of formation. So the standard free energy of formation is the change in free energy associated with the formation of 1 mole of a compound from its constituent elements. So if we had water, for example, its constituent elements being hydrogen and oxygen, so the standard free energy of formation, it has to do with the free energy associated with its formation from the hydrogen and the oxygen. and the standard free energy of formation of most stable forms of elements is 0, for example O2, which has a standard free energy of 0. So this equation should look familiar. It's very similar to the one that we just used when calculating the standard molar entropies. The only difference is, in this case, we're using standard free energies of formation, or delta G formations. So let's do a quick calculation and try to determine the delta G of formation for the reaction below using the information that we're given. So since we're calculating the delta G of reaction, we know we need to use this equation down here. And then now all we have to do is to plug in the values that were given to solve for delta G of reaction. So if we plug in the numbers and solve for delta G reaction, we get a number of minus 5,798.2 kilojoules per mole. And what this is telling us is that since we solve for delta G of the reaction at standard state, so that little 0, which is called naught, stands for standard state, that this reaction at standard state conditions is going to be spontaneous. So it's going to run in the forward direction. It's going to create carbon dioxide and water. Now, if you look at it more closely, you might recognize this as a combustion reaction. We have an organic molecule plus a bunch of oxygen creating carbon dioxide and water, and those reactions are definitely spontaneous. So when we're talking about spontaneous processes, we have to realize that a reaction is going to be spontaneous in one direction, but not spontaneous in the other. So if we look at water as an example, if we have a block of ice and put that at room temperature, we all know that that's going to spontaneously melt. But water put at room temperature is not spontaneously going to turn into ice. So that's one reaction being spontaneous, the forward reaction of ice turning into water, but the reverse reaction, water turning back to ice, is non-spontaneous. So let's look at that in terms of our equation, delta G equals delta H minus T delta S. And we're going to look at it over a temperature of about 20 degrees. So from minus 10 to plus 10 degrees Celsius. So this graph shows both delta H and our T delta S terms. Now over the range of minus 10 to plus 10 degrees Celsius, the value of delta H for water is not going to change very much. And that is shown by the nearly flat green line. But the T delta S term is going to change quite a bit. First of all, because the temperature itself is changing, and as we increase the temperature, the entropy of water is also going to increase, especially when it goes from being a solid to being a liquid. So if we're looking at the reaction of ice melting, then we can see from this diagram that it's going to be non-spontaneous below 0 degrees Celsius, or below 273 Kelvin. And that's because the T delta S term is smaller than delta H, as shown by the purple line. So every spot here on that purple line is lower than delta H. So when we take delta H and we subtract T delta S, then the value of delta G is going to end up being positive. So that's a non-spontaneous process. Above 273 Kelvin, T delta S is now larger than delta H. So when we subtract T delta S from delta H, we're going to end up with a negative number for delta G, which means that's a spontaneous reaction. So right at 273 Kelvin is where those two lines intersect. So that means that the values for delta H and T delta S are equal. So in that case, delta G would be 0, and that would mean that we have a reaction at equilibrium. So at 0 degrees Celsius, that's where the phase change is occurring from ice to water. So we have an equilibrium between ice and water at 0 degrees Celsius. So from this, you can see that temperature matters for determining whether or not a reaction is spontaneous in the forward direction or not. So this chart here shows you the signs of delta H and delta S that would result in a reaction being spontaneous, not spontaneous, or temperature dependent. So if we have delta H as negative and delta S as positive, that reaction is always going to be spontaneous because the resulting delta G will always be negative. If delta H is positive and delta S is negative, then delta G is always going to be greater than 0, so that reaction is always going to be non-spontaneous. And if we have a situation where delta H and delta S have the same sign, so either they're both positive or they're both negative, then it's going to be temperature dependent. If they're both negative, then the reaction will be spontaneous at lower temperatures. Now, there's no specific cutoff for what lower temperatures means. It's more of a relative term. And if both delta H and delta S are positive, then the reaction would be spontaneous at higher temperatures. So that's all I have for this section. As always, please let me know if you have any questions.